stability analysis of infinite slopes. Sorry for some dull picture here. So you can see here, so this is the AB which represents the slope surface, and CD it will represent the critical surface. Here we are going to consider a soil wedge, or you can say a prism here like this. So having sloping distance B and depth is equal to Z. The slope angle is I here. So I can take the component here like this, B cos of I. So this is the sigma Z, it is a vertical stress acting at this point. Okay, now we see this. So horizontal length of prism is B cos I, already I said it here. The volume of per unit length of prism. So volume is area multiplied by unit thickness. So I can calculate the area of this. So this is B cos I multiplied by Z. So it is just like a trapezoidal rule we are using here. So Z into B cos I. So this is the weight, this is the depth. The weight of the prism. So this volume multiplied by the gamma here. So gamma is the unit weight of this soil. So gamma multiplied by this volume. So this will give the weight of the prism. Vertical stress sigma Z on surface CD. So we are going to calculate now the stress value. So this is the weight here. So weight divided by area. So that is a force upon area. So this will give you sigma Z. So force is W and area is B multiplied by unit thickness. So you see it is perpendicular to this surface here. So B into 1 here. So this is the area. So putting all the values of W and this area, I will get gamma Z B cos I divided by B. So B get cancelled out and we get the sigma Z is equal to gamma Z cos I, where sigma is the normal stress component, sigma Z cos I, and tau is the tangential stress component, sigma Z sin I. So I can see here, so this is the result here. So this is perpendicular to the surface and this is parallel to the surface CD. Okay, sigma gamma Z cos square I. Now I am getting the sigma value. Sigma Z I can put gamma Z cos square I. So gamma Z cos I multiplied by cos I. So this will become cos square I. And sigma Z sin I, this is the tangential component. So tangential component tau is equal to sigma Z value. Gamma Z cos I multiplied by this sin I here. The tangential component tau is called the shear stress, which induces the failure along the CD and resisted by the shear strength tau F. So tau F, it is the capacity of the soil, and tau, it is the shear stress developed in the soil due to this prism here. So this is the prism and it causing the stress due to self-weight only. So whatever the stress is developed, it is due to self-weight and it will be resisted by shear strength of the soil. Now what is the factor of safety of slope against the sliding due to shear is equal to shear strength divided by actual shear. So this ratio will give you the factor of safety here. Now we can see the cases one by one. So this is a case number 1, that is a cohesion ratio. So we are going to use this condition in case of cohesion ratio. Now this is this stable slope. A slope is provided with angle equal to I, and let's assume our soil is having phi value, angle of internal friction phi here. So this is the strength element. As it is a cohesion-less soil, our equation C is equal to sigma plus tau is equal to C plus sigma tan phi. So C will be 0 here, correct, because it is a cohesion-less soil. So this will represent C is equal to 0. So this line will start from the 0 itself. And this red line, it indicates the unstable soil. So whatever the phi is greater than I value, so slope value is greater than phi value, so it becomes unstable. So here you can see O is the failure envelope for the cohesion-less soil defined by the equation tau F is equal to sigma tan phi. So here C plus sigma tan phi, so C value is 0. So we are getting tau F is equal to sigma tan phi. The OB represents the locus of the stress component sigma and tau acting on the critical surface CD for various values of the Z here. Now I can take the ratio here. If I take the value of sigma divided by tau, I will get the cos I divided by sin I, that is a cot I. Thus the line OB drawn at the inclination of I with the sigma axis represents the equation sigma is equal to tau cot and tau I is equal to sigma tan I. So I can get the relation factor of safety like this. Tau F is equal to FOC is equal to tau f divided by tau, so it is tan pi upon tan I. So once again we will go through this figure so that you can understand very easily. Let's suppose this is the slope surface and this is the strength. Okay. Now I am going to apply some stress over here. So this is the stress line and this is the shear stress line. So this is the stress developed. So this is the sigma. Whatever the stress is developed due to self weight is here. So I can draw a line here like this. If I draw a line like this, I will get the x value as sigma for stable slope. Similarly, same value is applied for the strength envelope sigma. But there is a difference of shear stress and strength envelope here. So I can see like this. So this is the tau and this is the tau f. Now I want the factor of safety. So this is the tau f divided by tau. So you can see here for all these points tau f is always greater than tau. Tau f is always greater than tau. See here you can take. If I apply this sigma here, so this is tau f. If I apply sigma like this, so this is tau and this is tau f. So all the time tau f is greater. So if I take this ratio, factor of safety is equal to tau f divided by tau, what will happen? This value will be always greater than 1. Correct? For stable slope, factor of safety must be greater than 1. So I can say, so for any value of this slope angle I, the factor of safety is greater than 1. So this is the stable slope. But if I provide angle equal to this one, angle is like this, now this is I, and I draw this line, what will happen? So tau will be greater than tau f. So this value will become less than 1. So our conclusion is like this. If I make slope angle less than phi value for cohesion-less soil, my slope will be stable. If I made my slope equal to phi, what will happen? My slope is at very critical stage. So factor of safety will be 1. And if my I value is greater than phi, my slope will be unstable. Now same will be, you can see here, what is tau here? Tau is this one. So I can take the slope here. So slope of this is tan I and slope of this is tan phi. So same is represented here in this equation, and we are getting this equation for cohesion-less soil. Factor of safety is equal to tau f divided by tau, that is the tan phi upon tan I. So this is the factor of safety. So I can say here conclusion that if I is less than 5, then for cohesion-less soil, slope is stable. Now cohesive soil is having strength envelope is like this. Tau f is equal to C plus sigma tan phi. So sigma tan phi we already seen. So sigma tan phi, it represents a strength envelope like this. If I make the C value 0, it will start from point O here. But there is an intercept, y-intercept C is present, C value is present. So I can draw the strength envelope from here. So this is the C, this is the phi, and this is the strength envelope of soil. Now the same case, if I provide the slope value equal to phi, what will happen? So these two lines will become parallel to each other. So this line will never intersect this line. So this is the slope line and this is the strength envelope line. Then what I can say, if I provide the slope angle I less than phi or equal to phi, my slope will be stable in case of cohesive soil. But if I increase the phi value, increase the I value greater than phi, what will happen? My slope line will intersect the strength envelope at a particular point. Let's say it is a point F. So this slope parallel or less than phi is stable. But if I make the phi I value greater than phi, what will happen? It will intersect at certain point, let's say F here. So this point is very critical here. So below this point, my slope is stable. At this point, it is a critical, and beyond this point, this will become unstable. Now I want to take care about this portion only. And now I want to identify what is the factor of safety below this level. So below this point, below F, or what is the stress value below which my slope is stable. So this is my objective. So see here, if I is less than phi and represented by line OB like here, and no critical state of stress is reached and slope will be stable. So I is less than or equal to phi, my slope will be stable here, as already said. If I is greater than phi, represented by the line OF, it will cut the strength envelope at some point F and state of failure is reached. So this is the point where you can say tau F divided by tau will give factor of safety is equal to 1, and this will be critical stage. Okay. For any depth z less than represented by point F, tau must be less than tau F and slope will remain stable. So that is the same point I have told already. So we are going to calculate the factor of safety for the points below the F. Okay. So in figure, point C1 is stable for the slope of angle I greater than phi. Hence, if I, let's see here, so this is the point C, you can see. So at this point tau F is greater than tau, so this is a slope stable. So we can say the C2 point, whatever the stress is developed, is safe for particular angle this. Okay. So for this we are going to derive a relation. Hence, if I is greater than phi, the slope can be stable only up to the limited depth known as the critical depth here. So I can write the equation, factor of safety tau F divided by tau. What is tau F? C plus sigma tan phi, and tau is tau. What is sigma? Gamma z cos square I. It is already seen here. Tau gamma z cos I sin I. So we are going to put all this in this equation. So we are getting this equation right. For critical depth, we can replace the z with the HC here. Correct? So this will become critical height. So corresponding point to the factor of safety. And this is the point, critical safety, where factor of safety is equal to 1. Correct? So this is the critical height below which we can say the factor of safety is greater than 1 and all these stable values here. But this point, factor of safety is equal to 1 because tau F is equal to tau. And we are representing that height equal to HC here. Correct? Got it? So we are putting this value F equal to 1 and Z is replaced with the HC here. Let's see. Now we are going to rearrange all this equation. So whatever the denominator part will be there, I have multiplied here on one side and we are getting this. We are taking the common point HC here and rearranging all these things here like this. Now I have taken the HC divided by gamma HC on the left hand side and remaining on this side. The dimensionless quantity C upon gamma C. The unit of C is kilonewton per meter square. The unit of gamma is kilonewton per cubic meter and HC is meter. So meter and in kilonewton per cubic meter, 1 meter is gone, so it is again kilonewton per meter square. Kilonewton per meter square upon kilonewton per meter square, it is a dimensionless quantity. And this dimensionless quantity is called the stability number Sn. So this is Taylor's stability number. So I written C divided gamma C is the stability number Sn. Okay, let FC represents factor of safety with respect to cohesion and Cm be the mobilized cohesion at depth h. Then it is given by Cm is equal to C upon Fc, and again I can rearrange with the help of C and Cm and Fc. So arranging all this value, I can get the different equation like this. So Sn is equal to C upon gamma C, putting the value of C, Cm upon gamma h, or again rearranging for the Fc, C upon Fc gamma h. So you can use any of this equation to get the values of Sn or factor of safety with respect to cohesion or mobilized cohesion. But better understanding, you just remember this equation, Sn is equal to C upon gamma hc, as well as this one, Fc is equal to Hc upon h, critical height divided by height of the slope here. Okay, so this is called Taylor's stability number. Thus the factor of safety with respect to cohesion also represents the factor of safety with respect to height. Using the friction circle method and analytic procedure, Taylor's determined the value of the Sn for the finite slopes. It assumes factor of safety with respect to friction is unity, that is the friction term is not included in this. So finally you can say, so this is the expression for the factor of safety of the cohesive soil This is the stability number for cohesive side, and this value depends upon the slope value and the phi value.